Hey, everybody. It's Friday, June 4th. And as you can see here in the aim today, our goal for today's video is all about how we can describe wave phenomena experienced by light waves. Now, as we said in a previous video, wave phenomena are things that waves do. And one of the most important physics debates in the late 1700s, early 1800s was about whether or not light was a wave or a particle. People like Isaac Newton thought it was a particle. Other scientists had an inkling that it might exhibit some wave properties. Now, as we've already talked about so far in this course, we kind of spoiled this debate a little bit because we have been pretty clear so far that not only is light a wave, it is in particular a transverse wave. All of these waves we call electromagnetic waves can be characterized as transverse waves. And so what I want to cover today in this video is a bunch of different wave phenomena that are particularly important for light, and then sort of go through the settling of that debate as science progressed through the late 1700s and early 1800s. So I want to be clear about one thing. The wave phenomena we are talking about today are absolutely demonstrated and exhibited by all kinds of waves. That would be light waves, sound waves, water waves, even, or any other kind of mechanical wave. These wave phenomena are experienced by all kinds of waves. But when it comes to the conversation about light, it is particularly important that we discuss these wave phenomena in particular. Because we are talking about a lot of wave phenomena, I kind of want to go through them quickly. So let's just jump into it. The first wave phenomenon, remember, phenomena is the plural of phenomenon, is diffraction. Now, diffraction is a fancy name for something quite simple. Diffraction is a process during which waves spread out after they move through an opening in a barrier. Now, what happens when waves approach a barrier, essentially, is that the barrier now acts as a source for all of the waves, and the waves spread from that source in a fairly predictable way, which we're going to talk about here on the next slide. But basically what you need to know and get out of this slide is that diffraction is a process during which waves spread out after they move through an opening in a barrier. And this happens because the barrier effectively operates like it is a source of a wave. Take a second to pause this video here and write that down. And when you hit play, we'll explain this in a little more detail. Now, there are two kinds of diffraction that we talk about in this course. One of them is called single slit diffraction, and one of them is called double slit diffraction. And so I want to very briefly here talk about single slit diffraction. So what we see for single slit diffraction is that we see these wave fronts, usually represented by straight lines, coming toward an opening in the barrier. And like I said, the opening in the barrier effectively serves as a source for these waves. So as the front wave gets very close to the barrier, effectively what happens is the empty space in between the barrier functions as a source for new waves. And since there's no obstructions or anything to get in the way on the other side of the barrier, what we see is that these wave fronts spread out in like this semicircular kind of pattern on the other side of the barrier. That's because this point right here in between the barrier is effectively serving as a source for new waves. Those waves are effectively spherical, which we can say in simpler language as semicircular wavefronts. So single slit diffraction happens when planar wavefronts pass through a single opening, which is approximately equal to their wavelength. They diffract into semicircular wavefronts. Basically, what diffraction is then is just kind of like the bending of these sound waves. Now, you've actually seen this before in your life. If you've ever been sitting in a room and heard somebody talking to you from outside of the door, then you've experienced diffraction. Because what happens is those sound waves approach the opening in the door, and then when they get to the doorway, which is the opening in the barrier in this example, they spread out throughout the entire room. So if you've ever been sitting in a room that has a doorway and the door is open, and you've heard somebody talking outside of the room, then you've experienced the diffraction of sound waves. Now, what we should also say here, these are just key facts, not overly important, but they're true nonetheless. The amount of diffraction, which is really like the amount of bending, like how much these things get bent, depends on the size of the opening in the barrier and the wavelength of the waves. So essentially, how close together these things are, and by these things I mean like the two sides of the barrier, compared to the wavelength of the waves, keeping in mind the wavelength of the waves here would be represented by the distance between these two lines, that ultimately determines the amount of quote unquote bending. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, so here's a better drawn picture of single slit diffraction. Notice here we have these planar wavefronts on the left-hand side of the diagram here. They are approaching the opening in the barrier. You can see here that the wavelength is approximately equal to the width of the barrier. And then we see they diffract or bend. And I'm going to actually write here, diffract/bend into semicircular wavefronts. That's the basic idea behind diffraction. We just see these planar wavefronts get bent. All the while, the wave is still traveling to the right. This picture, frankly, is really all you will ever be asked about. So take a second to pause this video here and sketch this in your notes. And when you hit play, we'll move on. All right, so this is not really like critically important for you to know, but I do think it is just interesting to look at so you get a sense of exactly how this works. This picture is basically showing you how the opening in the barrier and the wavelength affect the amount of diffraction. Remember, what we mean by the amount of diffraction is the amount of bending. And so if you look here, we see a very large opening for a relatively small wavelength. Notice here you could fit many of these wavelength lines in between the opening and the barrier. We see low levels of diffraction. Notice here they're using the word aperture. Any of you who are interested in photography might know what that means. But if you don't, the word aperture in this context basically just means the opening. The reason why I said anybody interested in photography might know this is because the amount that basically the photo sensors on a camera get opened ultimately affect what kind of picture you take, how much light gets in and how much exposure of the film, or obviously if you're using a digital camera, then like the exposure of the sensor you get. Of course, as we showed before, if you have a small opening and a small wavelength, you get high levels of diffraction or bending. It bends a lot. One way I think it's important to think about it, even though it's a little scientifically inaccurate, it's just like a fairly good mental model, is that these planar wavefronts are kind of getting like squeezed through the opening. And if you squeeze them through the opening, they're going to have to curve to be able to get through. And that's why we see these high levels of diffraction. And notice here, we have a large opening, a large aperture, but we also have a large wavelength. It's all about how the size of the wavelength compares to the size of the opening. Here we had a super big opening, but a tiny wavelength. They weren't matched well. It doesn't bend as much. It's okay that we have a large wavelength here because we have a large opening. Large opening, large wavelength, a good amount of diffraction. That's the idea. Don't go nuts about this image. You don't need to sketch this in your notes. Just a good thing to keep in mind. That's really all you need to know about single slit diffraction. Let's take a look at a problem. This problem is from the Wave Phenomena packet on page 13, number 6. It says, which diagram best represents the shape and direction of a series of wavefronts after they have passed through a small opening in a barrier? I want you to take a second to pause this video here and take a look at this problem. What is wrong about the images that are shown here, which are not the answer choice, and what makes the correct answer choice correct? Take a second to pause this video here, figure out the answer, and when you hit play, we'll go over it. All right, really all you need to know in order to answer this question is what the definition of diffraction is. The definition of diffraction is basically the spreading out of waves as they approach and pass through a small opening in a barrier. So notice I just said here, the waves spread out. That means choice 1 is definitely wrong. This shows these wavefronts here getting closer together with these arrows. That is not correct. Notice it's the same thing for number 3. Actually, number 3, in fact, shows the wave changing direction, which really makes no sense. That's out Notice 2 as well shows these waves here getting closer together instead of spreading out. That's wrong. The answer here is 4. Diffraction occurs when waves approach an opening in a barrier and then emerge from the other side. Another important thing to notice about these well-drawn diagrams here is they've even preserved the wavelength. The wavelength of the wave stays the same when it passes through the opening in this barrier. That's the basic idea. It simply just spreads out in a different pattern. It comes in, these wavefronts come in straight lines, and then they spread out in a semicircular pattern. Let's take a look at how that works in the real world. So in this video here, we have a device called a ripple tank. And this ripple tank is basically just a device that's going to generate ripples in this water. Notice here we have an opening in a barrier, a single slit diffraction experiment. Now they're going to show us a view of this basically through like a projection on a mirror. And notice here when we have a narrow slit, you can very clearly see that that flat plane wave generator, let me just go back to that, is going to generate plane waves, which are those flat wave fronts. And when they pass through the opening in the barrier, notice they emerge in a semicircular pattern. That's really it. Now, what they're also going to show you here is they're going to make the slit wider here. And as the slit gets wider, notice we can't quite see those semicircular patterns as much. You can still obviously see there's a little semicircular nature to it, but as they increase the frequency, which is going to decrease our wavelength, we're going to get that kind of mismatch, and this thing just gets all kind of jumbled. It's not really that clear of a picture anymore. As they continue to increase it and increase it, you can see the ripples, you can see they get their semicircular nature, but the thing just gets all kinds of jumbled. And that's it for single slit diffraction. Now, of course, there are many other examples of diffraction, which we should probably talk about, and double slit diffraction is another good example of diffraction. Now, let's just go through this quickly here. Double slit diffraction occurs when planar wavefronts approach 2 adjacent openings in a barrier. That's why they call it double slit diffraction. So in this kind of example here, we have our planar wavefronts, but instead of them approaching a barrier that has 1 hole, it approaches a barrier that has 2 holes. And so what we see is something a little different. The waves, when they get up to these 2 adjacent openings in the barrier, they'll diffract through both openings or through each opening, and then they'll overlap. What happens when they overlap is quite interesting. So take a second to pause this video here, write that down, and when you hit play, take a look at an image here, which will explain what happens. All right, so the key detail here about double slit diffraction is that we said the waves are going to diffract through each opening, and then they're going to overlap. Now, when you see an image like this, which notice is showing these planar wavefronts approaching these 2 openings, and then bending into these semicircular wavefronts, or then diffracting into these semicircular wavefronts, when you see 2 waves overlapping, that should make you think of something we've already talked about this year. When you see the peak of one wave lining up with the peak of another wave, or the peak of one wave lining up with the trough of another wave. Keep in mind the troughs here are shown by these empty spaces in between. That should make you think of something. Double slit diffraction is a really important wave phenomenon for us to discuss in this course. And that's really because it's sort of like a double or combination wave phenomenon. Because after the waves diffract through the opening in the barrier, they overlap and interfere. And that's a really, really, really important thing to pay attention to. When these waves overlap and interfere, they experience both constructive and destructive interference at various locations in the medium. When the peaks overlap with the peaks, or the troughs overlap with the troughs, you get constructive interference. When a peak overlaps with the trough, or the trough of one wave overlaps with the peak of another one, you get destructive interference. And that's a very important thing to keep in mind. So let's actually just go ahead and write that down. Peak and peak, slash trough and trough. That gives you constructive interference. We either get bigger peaks or bigger troughs, or when we get a peak and a trough, then we get destructive interference. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, now, of course, why is this an important thing for us to discuss? Well, in 1801, a physicist named Thomas Young performed what is now known as the double slit experiment with light. Since light, experienced this double slit diffraction phenomenon and interfered, and only waves can experience diffraction and interference, Young demonstrated that light behaves like a wave. This is a very important piece of experimental evidence to show that light is a wave. The fact that light experiences double slit diffraction, which means it diffracts and interferes, is a great piece of evidence for the fact that light is a wave. Take a second to pause this video here and write this down. And when you hit play, we'll take a look at an example of that. All right, so let's take a look at an example of double slit diffraction. A good video here to show us double slit diffraction. We have here a good video from YouTube that I found where this guy shows it. Notice this yellow thing is a laser, and he's shining it at a device called a diffraction grating. And a diffraction grating is basically just a series of slits in a screen. So notice he's going to show the light going through the diffraction grating, and then he's going to take it away. He just took it away right now. And so when he shows you the screen, he's just saying, you see the laser on the screen? That's just a dot. The dot is basically just a laser beam on the screen. That's what it looks like when there is no grating or slits in front of the beam. Now notice he's placing the slits back in front of the beam. And when he's showing it on the wall, we see what we generally call our classic double slit diffraction pattern. Notice here, we see dark spots and bright spots. So here, for example, is a bright spot. You either have a peak overlapping with a peak or a trough overlapping with a trough to give you constructive interference. This interference that's taking place right here is constructive. But notice also at certain points like here, 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 and here, there are dark spots. And all over here, we see light canceling out light. That would be an example of destructive interference. It seems like a very counterintuitive thing. How could you possibly take light, add light, and end up getting no light? Because light is a wave, and it can experience destructive interference. This kind of pattern is known as a classic interference pattern. It is what we see whenever double slit diffraction occurs. That's the basic idea. And so what you need to know is that because light can experience this kind of phenomenon, that lets us know that it's a wave. Just very quickly before we move on, I just wanted to show you, here is an example, basically just a bigger version of what this guy was holding in front of that beam. We actually have one of these examples at school. It's an interference and diffraction set. Notice here, it's basically just a series of slits of various sizes. You can very clearly see that this row is a double slit set. And notice basically just the spacing between the slits is getting smaller and smaller and smaller as you go up and down. Pretty cool. All right. And with that, that brings us to our next wave phenomena, one that is particularly importantly demonstrated by light, wave reflection. Now, wave reflection, I'm sure, is something you have seen in your life. If you've ever seen a light wave bounce off of any surface, then you have seen reflection, specifically that adheres to the law of reflection. Now, there's a couple things we need to say about this before we move on. When we are showing reflection in physics, we draw these diagrams, and there are diagrams that we use to draw this called ray diagrams. We really only need to say a couple things about them. We need to say, first, ray diagrams show the direction of wave motion, and they're drawn perpendicular to the wave fronts. So what we should really say here, and I'm actually going to show you an example, is that when we draw this, notice that's pretty simply a ray diagram. It's a line, and it has an arrowhead, which is showing you the direction of the wave motion. It means this, which is, there's our arrow, and it's drawn perpendicular to our wavefront. So earlier in this video, you saw me draw a diagram like this, which was representing wavefronts. That's basically what this means. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, whenever light reflects, it obeys the law of reflection. Now, of course, the question is, what is the law of reflection? The law of reflection is the easiest thing we're going to talk about in this class this year. The law of reflection says the angle of incidence equals the angle of reflection. Now, here's a new piece of vocabulary. The word incoming is a good synonym for incident. So when we say the angle of incidence, we mean this is the angle the incoming light wave or the light ray is coming in at. And when it bounces off, those angles have to be equal. Now, that's not a great drawing there because it's not quite symmetrical, but you get the idea. The incident ray is the incoming ray. The reflected ray is the ray that bounces off its reflected. So that's pretty much it. That's all you need to know about the law of reflection. Now take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, moving on here. There's one more important thing we need to say about the law of reflection. First, we can say here this equation is shown in the reference table for the law of reflection. Pretty basic. The angle of incidence is equal to the angle of reflection. There's not much to it. I'll show you in the reference table later. The second thing that we should say, though, which is like really, really, really important, is the angles of incidence and reflection are always measured from the normal. And now, if you remember back to the beginning of the year, when we were talking about the normal force, we said the word normal is a mathematical term, which means perpendicular to the surface. So the normal, in this case, is a line drawn perpendicular to the surface. This is what any law of reflection representation is going to look like. So we see our line drawn perpendicular to the surface. This is our normal line. And we see our incident ray or incoming ray and our reflected ray. And what the law of reflection says is the angle of incidence is equal to the angle of reflection. Now I'm going to erase this part here in a second, but notice this angle is not the angle you want. The angle you want in these kinds of problems is always measured from the normal. This diagram is absolutely critical. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at a problem. All right, let's take a look at a problem. This problem is in the wave phenomena packet. It's on page 1, number 5. It says, the diagram below represents a light ray reflecting from a plane mirror. The angle of reflection for the light ray is. Pretty straightforward question. Take a second to pause this video here. Figure this one out. Come up with an answer. Come up with an explanation. When you hit play, we'll go over it. Okay. 65 degrees is not the answer to this question. I hope many of you realize that. 65 degrees is the angle shown to you in the problem. 65 degrees is not the angle of incidence here in this problem. It's very important to remember the angle of incidence and the angle of reflection have to be measured from the normal. And this angle is not measured from the normal. It's measured from the surface. Now, there are a few key pieces of information that you need to recognize. The normal is always perpendicular to the surface. That's a right angle symbol. It's just shown huge, so I'm not getting in the way here. That means you can always use the angle measured from the surface if they give it to you to figure out what the angle of incidence is. Because notice, 65 degrees plus the angle of incidence, theta with the subscript I, has to add up to 90 degrees because, you know, these angles are complementary. And so that's really it. If 65 plus the angle of incidence has to be equal to 90 degrees, then we can figure out here that the angle of incidence is going to be 25 degrees because 25 plus 65 gives us 90. And so here's the deal. Not that complicated. If the angle of incidence is 25 degrees, then that means the angle of reflection is also 25 degrees, which makes the answer to this question here choice 1. Take a second to pause this video here, write that down. When you hit play, we'll move on. All right, so we've kind of been flying from topic to topic in this video, and unfortunately, that's just the way this has got to go because we're trying to wrap up this unit here. So far, what we've said is that we know that light is a wave because it diffracts. There are two types of diffraction, double slit diffraction and single slit diffraction. Both of them basically involve light waves getting bent when they squeeze through an opening. If there are two openings, the light wave gets bent or diffracts through both openings, and then they interfere. Another thing light does, which is also things all waves do, is reflect or bounce off of surfaces. When waves reflect off of a surface, you will almost always see these with light waves though, they do so in like a symmetrical way, meaning the angle of incidence is always equal to the angle of reflection. That's just the way it is. The last thing we are going to talk about for today is the speed of light. I want you to write this under the heading light speed. And so we're going to ask a series of questions. First question we're going to ask here is, what determines the speed at which a wave travels? This is review. We've actually already talked about this so far this year. What determines the speed at which a wave travels? And we said the speed of a wave is determined by the medium in which it travels. Remember, we said same speedium, same medium. And so the speedium is determined by the medium. How can we make sense then, if the speedium is determined by the medium, how can we make sense of the fact that light travels at different speeds in different materials? Well, since all materials have atoms packed together in different ways, depending on which material it is, the fact that light will have to interact with those atoms means it won't travel as fast in those materials as it does in a vacuum. A vacuum is purely empty space. So when it doesn't have to interact with any atoms, it should make some logical sense that it's going to go faster when it doesn't have to interact with any atoms. Okay, very important for you to remember. The fastest speed at which light, or anything for that matter, can travel is equal to the speed of light in a vacuum. Now, when we say things like the speed of light, we often leave off the in a vacuum part. Light travels at different speeds in different materials. That 3.00 times 10 to the 8 meter per second number, that's the speed of light in a vacuum. And that's a very important thing to understand. Take a second to pause this video here and write that down. When you hit play, we'll move on. All right, moving on here. Another question we can ask, well, how can we describe the relationship between the density of a given material and the speed at which light will travel? We already kind of got at this directly already. We said if there are no atoms in the material, then light is going to travel the fastest it could possibly travel, which is the speed of light in a vacuum, 3.00 times 10 to the 8 meters per second. If there are some atoms in the material, then it's going to go slower. Well, the basic idea is, well, if there are more atoms in a certain amount of space, because remember, density is really just mass over volume. If there's more mass in a certain amount of volume, right? I can't really draw a cube, but let's just all pretend that that's like a well-drawn cube. That's not terrible. If there are more atoms inside of this box, then it's got a higher density. And if there are more atoms in there that the light has to interact with, then it should make sense. It's going to go slower. Light is going to travel slower in materials which are more dense, since the closer spacing of the atoms is going to offer more resistance to the motion of the light. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, there's a measurement for how much slower light is going to go when it travels from one medium to another. And that number is called the absolute index of refraction. The index of refraction, which is usually what we say, it is technically called the absolute index of refraction, but we almost always just say the index of refraction. It roughly gives us an idea of the density of the material. The higher the density, the higher the index of refraction. The formal definition of the index of refraction is pretty straightforward. The index of refraction for a given material is defined as the ratio of the speed of light in a vacuum to the speed of light in that given material. Effectively, what it tells you is how much faster light goes in a vacuum than it does in that material. So let's say the index of refraction for a certain material is 2. That tells you light goes twice as fast in a vacuum as it does in that material. That's really it. A couple other things to know. The symbol for the index of refraction is n, lowercase n. And what we can also say here is since the index of refraction of a material is inversely proportional to the speed of light in that material, right? If we have a slower speed, we're going to have a higher index because that means light is going that many more times faster in a vacuum. The higher the index of refraction, the lower the speed. And this tracks with everything that we said about density. And that's an important thing to keep in mind as we're moving along here. Now, we are going to show the equation in a second, but it's a good thing to pay attention to the fact that the index of refraction is just a ratio. It tells us how much faster the speed of light is in a vacuum than it is in any material. Take a second to pause this video here and write that down. And when you hit play, take a look at the equation. All right, let's take a look at the equation. Remember, the index of refraction is the ratio of the speed of light in a vacuum to the speed of light in a material medium. As we already said, the symbol is n. That means the equation is n equals c over v. Notice here, we just said this is a ratio of the speed of light in a vacuum to the speed in that material medium. So c here is the speed of light in a vacuum. That's measured in meters per second. And you always know that number. V is the speed of light in whatever material you're talking about. And then n is the index of refraction. And I'm going to write here in parentheses for that material. So when you know the speed of light in a material medium and you plug that in as V, when you solve for n, that's the index of refraction for that material. It works the other way around. If you have to solve this for the speed, well, when you plug in the index of refraction for a specific material, then you are finding the speed in that material and in that material only. Now, of course, a good question for us to ask looking at the equation here is, what are the units for the index of refraction? What are the units for the index of refraction? You take meters per second for C, you divide it by meters per second for V, and there is no unit. This is a unitless number. I have been saying all year, it is very important whenever you are doing your calculations to write units next to the numbers. We have now come up with the second variable. There are only two variables in this course which have no unit. The coefficient of friction, because it's a ratio of the friction force to the normal force, and the index of refraction, because it's a ratio of the speed of light in a vacuum to the speed of light in a medium. That's it. These numbers are just ratios. They have no units. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, so if you look in your reference table, you will see this chart for indices of refraction. Keep in mind, the plural of index is not indexes, it's indices. So these are just showing you a bunch of different indices of refraction. Notice, for air, in the reference table, it's listed as 1.00 or 1. This is not actually true, but it is true to 3 significant digits. The index of refraction in air is actually like 1.000001 something, or whatever it is. It shows you that the speed of light in air is just a teensy little bit slower than it is in a vacuum. For our purposes, though, it's really not that much slower than it goes in a vacuum, and so we call the index of refraction in this class for air 1. Notice, you should have some sense by now, or probably have heard, that a diamond is an extremely dense material. Notice that is the highest index of refraction listed in the reference table. This is why diamonds sparkle so much, because when light travels from air into diamond or back from diamond into air, its speed changes a heck of a lot. And as a result, we see some fancy sparkles. So basically, you don't need to memorize the index of refraction for all of these materials because they are in the reference table, but it is important to know what's in there. Air, corn oil, diamond, ethyl alcohol, crown glass, flint glass, just 2 different types of glass, glycerol, lucite, fused quartz, sodium chloride, water, and zircon. Notice if we go to page 5 of the reference table in the wave section, you will see these 2 equations that we talked about so far today. Your angle of incidence equals your angle of reflection, and n equals c over v. The index of refraction equals c over v. Notice here, they list n here as the absolute index of refraction. And if you go up to page 2 of the reference table, you will see that chart. Notice it's right underneath the electromagnetic spectrum. We've got all the indices of refraction for all of these various materials shown here. And that's it. Let's take a look at a problem. Now, there are a bunch of ways these problems could be asked. This problem in the wave phenomena packet, page 9, number 36, says the speed of light in a piece of plastic is 2.00 times 10 to the 8 meters per second. What is the absolute index of refraction of this plastic? So notice here, they tell us the speed of light in the piece of plastic. That means that's the speed of light in the material medium. That's what we label as V, 2.00 times 10 to the 8 meters per second. The speed of light in a vacuum in this equation always gets the symbol C, 3.00 times 10 to the 8 meters per second. And we're looking for N, the index of refraction. N, according to the reference table, is equal to C over V. And so we just take the numbers and we plug them in here. This is pretty basic. We have 3 times 10 to the 8 meters per second over 2 times 10 to the 8 meters per second. And rather simply here, 3 over 2, notice the 10 to the 8s cancel, and so do the meters per second. 3 over 2 is 1.5. So the index of refraction for this piece of plastic is 1.5. That would make the answer here choice 4. Now, of course, I think it's a good thing to always ask the question, well, what does this mean? And remember, what this means is that in a vacuum, light travels 1.5 times faster than it does in this piece of plastic. Take a second to pause this video here and write that down. And when you hit play, we'll wrap it up for today. All right, and 2 quick things here very quickly before we go. The first thing we should say is that since nothing can ever travel faster than C, the speed of light in a vacuum will always be larger than the speed of light in a material medium. This also means that by definition, N, the index of refraction, has to be greater than or equal to 1.00. Now, I'm going to come back to this in a second, but I just want to be clear. Notice, if you accidentally took, instead of doing 3 times 10 to the 8 over 2 times 10 to the 8, if you did it the other way around, 2 times 10 to the 8 divided by 3 times 10 to the 8, you would have gotten 0.67. You should automatically know that that cannot be correct because the index of refraction, N, can never be smaller than 1. If it was smaller than 1, it would tell you that light travels slower in a vacuum than it does in that medium, which is not correct. The other thing I want to say, because I think that this is important also, is that if you are taking the equation N equals C over V, and you are solving it for V, you get V equals C over N. Every single year, what I see on the final exam is instead of people getting V equals C over N, people get V equals N times C. And since N has to be greater than 1, that ends up giving them a V that ends up being a number bigger than 1 times the speed of light, which ends up making V larger than C. And that is not possible. Please be careful with your algebra. If you solve this equation for V, then you get C over N. Take a second to pause this video here and write that down. And when you hit play, we'll wrap it up. All right, everybody, that is it for today. There are a couple of questions for you to answer after this assignment as a concept check, so make sure you go back to the Google Classroom page and check that out. But with that, that is it for this video and for the week. Enjoy the weekend, everybody. Have a good one.